The problem then goes on and asks us more in part B, so let's take a look at that now. So if the true average percentage were 5.6, and not the 5.5 we've conjectured in the first part, with an alpha level of 0.01 based on our 16 samples, what's the probability of detecting the departure from H0? So what's the probability of detecting a departure? Remember, our alpha risk was the probability we've already looked at. The beta risk would be the probability that we would accept the null hypothesis even if it were wrong. And in this case, so what's the probability of detecting that? So power equals 1 minus beta in our formulation. So we know we're going to be doing a power calculation and basically say, what is the power of this test if in fact the actual mu were 5.6 at an O1 alpha level? So let's take a look at how we would solve for the beta risk associated with that as we go through. Okay, so we're doing a beta risk calculation where the actual mu that we were given is 5.6, not 5.5. Now on a scale of 5.5, 5.6, they're only 0.1 apart. So think about this as an engineer, even before you do the calculations. These two numbers are not very far about, and power tends to increase as the real value gets farther and farther from the conjectured value. So these two values are fairly close together. So I actually don't expect this to have a very high power, but let's go through the calculations and see what we get. So the first thing I do is take my alpha and figure that out. Now we were told in the problem to do it at a 0.01 alpha. It's a two-tailed test. The hypothesis is not equal, so I have to use half of alpha. So the alpha that I'm concerned with, alpha over 2, is 0.005. And then I can take the norm's inverse of that to say what z would give me a 0.005. So the z I'm interested in is basically a 2.58 if I round that off as I go through. So let's change our graph now. Let's go back over to our basic graph and redraw that as we go through. So if I have a new curve now, okay, I've got a mu of 5.5. Okay, as I go through. That hasn't changed. That's still my conjectured value. And now if I take my z of 2.58 and my negative z of negative 2.58, this would be the associated alpha risk associated with that value as I go through. Okay, so that's what I've calculated so far, is what kind of value can I get out of my basic values. Let's go back now to our spreadsheet. So I know my z is 2.58, so if I now can say how much has that shifted relative to the original distribution that I had. So remember, the shift is always involved in coming up with what's happening in a beta curve. So what I have to do is I have to redraw a second curve. You can't have a beta discussion based on the same curve you had your alpha discussion. Because what if my mu is really 5.6? Now I've exaggerated the curve for effect, but if I bring this line down now, okay, the beta risk is everything between these two barriers, obviously, but that would not have been rejected. So the second one comes down here. On this tail, it's going to be inconsequential because I've basically shifted this curve to the right some. And I want to know how much have I shifted it in terms of z. So it's 0.1 in terms of the underlying number, but I need to know how much has it shifted in terms of z. So if I go to back to the text and take a look at some of the formulations for this, here are the formulas in our text for how I'm going to do this. And notice I've got this term that takes the mu that I've got and divides it by sigma over square root of n. So this term right here converts the 0.1 shift that we've gotten into the number of z's, the actual number of z-curve calculations that we do. So we're really talking a shift here. Now we're dealing with an alternative hypothesis, the third one here, that says not equal to. So this bottom formula is the one that we want. So we want to know the probability related to our original z plus whatever happens as a result of the shift, minus the one for the lower. And that minus is because we're looking at a split curve as we go through. So I can show you that on the graphic real quick. So the minus is because we've got this blend up here is going to give us the distribution to the left of this, and we've got a second tail here for the lower. We want the space in between. We want to know what the beta risk here is in the middle of the curve. So we'll take the number we get from the z distribution of this, which is everything to the left, and we'll subtract everything to the left here. What's in between those is the beta risk associated with what we're working on right now. So that's the range of numbers we want to go through. So basically what's happened is that this z-curve is not 2.58 anymore. So if I take a curve like this, okay, at 5.5, and again exaggerating it for effect, and move the curve over it so it's centered at 5.6. This distribution that I had here under this original curve, when I extend that line up to the new, is going to be obviously a much larger area. So as the shift curves to the right, I need to know what z value is from the original data relative to the new curve that I go through. So that's what we're figuring out here in our spreadsheet. And that shift is 1.33 sigma to the left. So in essence, I've shifted my curve 1.33 sigma. So therefore, I've enlarged my tails as I've gone through. So according to the formulas that we've got, we're going to take that value and we're going to add it to the 2 sigmas, z-scores that we already have. We're adding a negative number in this case, so the number is actually going to go down, but that's okay. The formulas work perfectly well as we go through. So when I do my calculation, what used to be a 2.58 becomes a 1.2 and a negative 3.9. So if we go back to our curve and indicate that, the 1.25 is now here. So this is now going to be, if I extend this line down, this is a z of 1.25. And this other one extends down, I forgot what its value was already, negative 3.91 as we go through. So negative 3.91 is our negative z on this side. So we're interested then in the probability being on either side of that curve now. So the 1.25 is going to leave a much larger tail than this 2.58 did on the upper side. So by shifting the data, we're taking advantage of the fact that everything to the right of this line would have been rejected under our original hypothesis. So even if the original hypothesis was incorrect, we would have rejected anything under this portion of the curve or anything under this portion of the curve. So we get that advantage here on the shifted curve. Remember, what we see is the top curve. What's real is the bottom curve. So we have the advantage that anything to the right of this line would have been rejected because it would have been above 2.58 on the original curve. So anything above 1.25 on this curve will end up being rejected as we go through. So we can go ahead and take the upper and lower z that we had and calculate the probabilities for that. So the probability of being to the left of that upper 1.24 is 89%. The probability below the lower is very small percent. So the beta risk is 89.3%. So 89.3% of the curve falls to the far side. So we end up with 89.3% of our curve represents the beta risk between the two tails that we have going on here as we go. So the power of a test is equal to 1 minus the beta risk. So we can take that last step, subtract that 89 from 1, and say the power is basically 11%. So we have a test whose power is 11%. There's an 11% chance that had the real mu been 5.6, we would have detected that based on our hypothesis that it was 5.5%. Not huge. We could do much better than that if we had a better curve to our fit. If the value had been 5.8, 5.9, 6.1, if the value had been farther away from the mean, the power would have gone up very dramatically for the same reason we saw, is that as things shift to the right, the area under the curve grows geometrically fast as things go through. But in this case, the answer would be 11% on our curve. And this 0.107 to the appropriate decimal place, I think they want 4 decimal places, so 0.1071 would be the answer you'd look for in the problem. That gives you the power of the test as a probability.